Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
You know, when we normally look up at the night sky, we see this flat, brilliant canvas. The stars, the moon, they all just look like they're painted on the ceiling of our world.
Right. That's a beautiful sight.
It is undeniably beautiful, but it feels incredibly distant, untouchable almost, like a backdrop to our lives rather than a place we actually inhabit.
Yeah, it really serves as the ultimate boundary line for human experience. I mean, for our entire lives, and truly for almost everyone on Earth right now, that sky has been a place we only visit in the very shallow waters of low Earth orbit.
Exactly.
We fly our planes in the atmosphere.
Yeah.
And, we send astronauts to space stations just a few hundred miles up. But the vast, deep ocean of the cosmos beyond that, that specific gravitational shelf has remained entirely untouched by human hands for over half a century.
And that is exactly what is fundamentally shifting right now. I mean, we are talking about humanity's imminent historic return to deep space. We are breaking out of low Earth orbit.
We really are.
We are going back to the moon. And we are doing it with the Artemis II mission. I'm feeling this palpable, almost electric excitement about this because, this isn't just another scientific deployment. This is a monumental shift in what it means to be a human being living in this solar system.
It's a complete paradigm shift.
But I have to ask, just to play devil's advocate for a moment here.
Sure, go for it.
We have been to the moon, we left footprints, we planted flags, we brought back lunar regolith.
No.
Why spend the immense political and financial capital to do it again? Like, what is the actual paradigm shift here, mechanically and philosophically?
Well, the paradigm shift lies entirely in the long-term intent. And the architectural approach, we are not repeating history. We are building upon it to create something entirely new.
Okay.
The Artemis program embodies a completely different era of lunar discovery.
Yeah.
I mean, think about the name itself, Artemis. In Greek mythology, Artemis is the goddess of the moon.
And she is the twin sister of Apollo.
Exactly. It beautifully honors the past while pointing to a very distinct, unique future.
I do appreciate the poetry of the namesake, but pragmatically, how does this modern twin differ from the Apollo legacy? Because Apollo was arguably one of the greatest technological sprints in human history.
It was a magnificent sprint, but it was driven by a very specific geopolitical context. The Apollo missions, for all their incredible, world-changing achievements, were focused primarily on rapid landings and rapid returns.
So getting there, proving we possess the technological capability to achieve it, and coming home.
Yes. The architecture was expendable. You used it once, and it was gone. Artemis, conversely, is an infrastructure project. It's about establishing the foundational architecture for a permanent, sustained human presence.
So we aren't just taking a daring weekend camping trip to the wilderness anymore.
Not at all.
We aren't just pitching a tent and taking photos. We are talking about surveying the land, laying down concrete foundations, bringing the lumber, installing the plumbing, and building a permanent research station.
That is a highly accurate way to frame it. Artemis aims to construct actual lunar habitats and reliable transportation networks in cislunar space.
Wow.
And the key to making this permanent cabin a reality is a concept known as in situ resource utilization, which is really the absolute cornerstone of modern deep space exploration.
Meaning using the resources that are already there rather than hauling everything out of Earth's gravity well, because the launch mass penalty for bringing every single drop of water and ounce of fuel from Earth indefinitely would be mathematically unfeasible, right?
Exactly. Launching mass from Earth requires immense kinetic energy just to overcome our gravitational pull. Every kilogram of payload requires many times its weight in rocket propellant just to reach orbit.
The tyranny of the rocket equation.
Yes. So if we can extract resources directly from the lunar environment, we fundamentally alter that equation. This is precisely why the geographic focus of the Artemis program is completely different from Apollo.
We are no longer targeting the equatorial regions of the moon.
Right. The focus is shifting entirely toward the lunar South Pole.
Okay, let's unpack that for a second. The lunar South Pole. From a geological standpoint, why is that specific region so incredibly valuable to a sustained human presence?
Well, we have discovered, through decades of robotic orbital reconnaissance, that the lunar South Pole harbors these unique geological features called cold traps.
Cold troughs.
Yeah. Because the moon's axis is only slightly tilted relative to the sun, the sunlight at the poles comes in at a very shallow grazing angle. This means that the interiors of deep craters at the South Pole, places like Shackleton Crater, have not seen sunlight for billions of years.
They are permanently shadowed regions.
Exactly.
And because there's no atmosphere to distribute heat, those permanently shadowed regions must be unimaginably cold.
They are some of the coldest places in the entire solar system, hovering just a few degrees above absolute zero. And over billions of years, comet impacts and solar wind interactions have deposited water molecules across the lunar surface.
But water at the equator would just instantly sublimate into the vacuum of space, right? Due to the extreme heat of the lunar day.
Exactly. But water that migrated into these cold traps at the poles became instantly frozen and locked in place. We now know there are vast reserves of water ice mixed into the regolith in these craters.
Water ice, that genuinely is the gold mine of the cosmos.
It really is.
But extracting it and utilizing it sounds like a monumental engineering hurdle. I mean, I understand that water provides vital life support. Astronauts need it to drink, to rehydrate food, for hygiene. But you're talking about using it for infrastructure. How do we turn frozen dirt in a pitch-black crater into multiplanetary infrastructure?
Through the elegant application of chemistry and solar power. Surrounding these permanently shadowed craters are elevated crater rims and mountain peaks that are bathed in near-constant sunlight.
The peaks of eternal light.
Yes, we can place massive solar arrays on these peaks to generate continuous electrical power. We then use that power to run rovers and extraction equipment down into the dark craters to mine the icy regolith.
Okay.
Once we extract the water ice, we melt it, purify it, and then subject it to a process called electrolysis.
Electrolysis. So running an electrical current through the water to break the molecular bonds.
Precisely. Water is H2O. By applying that continuous solar electrical current, we split the water molecules into their constituent elements, hydrogen gas and oxygen gas. We then super chill these gases until they become cryogenic liquids.
Liquid hydrogen and liquid oxygen.
Exactly.
Which are the exact high-efficiency propellants used by our most advanced rocket engines.
They are. So in mastering this single resource, the moon completely transforms from a scientific destination into an active, off-world fueling station.
That is incredible.
We can launch spacecraft from Earth with just enough fuel to reach lunar orbit, stop at a lunar gateway station, refuel the tanks with propellant manufactured entirely on the moon, and then proceed onward to Mars.
Wow.
The moon becomes the essential stepping stone, the proving ground for everything we need to accomplish to become a true multiplanetary species.
That is a staggering logistical vision. We are talking about setting up an operational industrial base on another celestial body. But taking that massive leap isn't just an engineering challenge, is it? It's a geopolitical one.
Highly geopolitical.
Because if there are limited peaks of eternal light and specific craters with high ice concentrations, how do we establish a multiplanetary infrastructure collaboratively?
That is perhaps the most crucial non-technical aspect of the Artemis program, and it is governed by the Artemis Accords.
Right.
The Accords are an international framework designed to ensure transparency, interoperability, and responsible exploration in cislunar space. It builds upon the foundation of the Outer Space Treaty of 1967, but modernizes it for an era where we were actually extracting resources and building permanent outposts.
I want to focus on that word, interoperability, for a second. For you listening, think about how your phone charger might not work on someone else's device. Now scale that up to spacecraft. In the context of deep space operations, what does interoperability actually look like between different sovereign nations?
It is the principle that our technologies must be able to work together seamlessly, regardless of which nation built them. It means agreeing on universal engineering standards.
Like standardizing the design of docking mechanisms.
Exactly. Docking mechanisms, environmental control systems, communication frequencies. If a spacecraft from one nation is out there in deep space, a vessel from any other participating nation must be physically capable of docking with them and rendering assistance.
It is a commitment to mutual aid and standardized safety protocols.
Yes, it is a highly collaborative diplomatic effort. The collaborative spirit driving this modern exploration is unprecedented. We are pooling global resources, intellect, and ambition to ensure that the expansion into the solar system is peaceful, sustainable, and beneficial to all of humanity.
And Artemis II is the critical crewed proving ground for all of this architecture.
Exactly. It validates the partnerships and the operational concepts that will make the subsequent surface landings possible.
Which brings us to the raw physical reality of actually getting off this planet to execute that vision. You can have the best philosophy and international agreements in the world, but you can't build a permanent outpost on the moon without a heavy lift launch vehicle capable of throwing massive amounts of hardware into deep space.
You need a heavy-duty moving truck.
Right. And that brings us to the colossal machine making this entire journey possible, the Space Launch System, or the SLS.
The Space Launch System is a towering achievement in aerospace engineering.
Yeah.
Specifically for the Artemis II mission, we are looking at its initial Block 1 configuration.
I'm looking at the thrust profiles and the physical dimensions here, and the numbers are genuinely difficult to process. How does the Block 1 configuration actually compare to the historic vehicles we are familiar with, like the Saturn V?
The scale and power of the SLS surpass the Saturn V in key performance metrics. The SLS Block 1 stands 322 feet tall.
Wow, 322 feet.
To conceptualize that, it is taller than the Statue of Liberty.
That is just massive.
It is, but height is just a function of tank volume. The true measure of a launch vehicle is its thrust, the raw physical force it can generate to push payload against the relentless pull of Earth's gravity.
And what's the thrust on this?
At liftoff, the SLS generates an astonishing 8.8 million pounds of thrust.
8.8 million pounds of thrust. That officially makes it the most powerful rocket ever successfully flown. I mean, the sound alone, the acoustic energy generated by that much power must be earth-shaking. But how exactly do they generate that specific amount of sustained force? Walk me through the architecture of this vehicle.
The architecture of the SLS Block 1 is elegantly designed to maximize both raw power and establish reliability. It utilizes a hybrid propulsion strategy.
Okay.
On either side of the towering orange core stage, you have two massive 5-segment solid rocket boosters, or SRBs. These provide the overwhelming majority of the thrust required to get the massive vehicle off the launch pad and punch through the thickest, lowest layers of Earth's atmosphere.
Now, I understand that solid rocket boosters are fundamentally different from liquid engines. Once you ignite the solid propellant, you are fully committed, right? There's no throttle dial.
That is correct, and it speaks to the incredible precision required in their design. A solid rocket booster is essentially a meticulously controlled, continuous chemical reaction. The propellant is a solid mixture of a fuel, typically powdered aluminum, and an oxidizer, like ammonium perchlorate, bound together in a rubbery consistency.
Right.
But the brilliant part is the geometry. The hollow core running down the center of the solid propellant is shaped like a multi-point star.
Wait, why a star shape rather than just a simple cylinder?
Because the burn rate, and therefore the thrust output, is directly proportional to the exposed surface area of the burning propellant.
Oh, so by shaping the core as a star, aerospace engineers precisely dictate the thrust profile over time.
Exactly. As the propellant burns outward, the star points burn away, changing the surface area and naturally tapering the thrust exactly when the vehicle approaches maximum aerodynamic pressure.
Which is the point in the ascent where the aerodynamic stress on the vehicle is at its absolute highest.
Yes. It is a brilliant, entirely passive method of throttling a solid rocket motor.
That is fascinating. It's essentially pre-programming the throttle into the physical geometry of the fuel itself. And these specific solid rocket boosters are heavily derived from the Space Shuttle program, aren't they?
They are. The Space Shuttle utilized 4-segment solid rocket boosters.
Mm-hmm.
For the SLS, engineers added a 5th segment, increasing the amount of propellant and therefore the total impulse. We are taking incredibly reliable, highly understood technology and scaling it up for deep space capabilities.
So those two 5-segment solid boosters provide the massive initial surge off the pad, but they burn out and fall away after a couple of minutes. What is powering the vehicle through the rest of the ascent?
That is the role of the massive core stage. The core stage acts as the structural backbone of the entire vehicle, and it primarily consists of 2 enormous tanks holding cryogenic propellants, super-chilled liquid hydrogen fuel and liquid oxygen.
And at the base of this core stage,
you have 4 RS-25 engines.
And the RS-25s are also legacy hardware from the shuttle era, right? These are the space shuttle main engines.
Exactly. They're widely considered to be among the most complex, efficient, and reliable liquid propellant rocket engines ever created.
I mean, the turbopumps inside those engines spin at tens of thousands of revolutions per minute, right?
They do, forcing thousands of gallons of cryogenic propellant into the combustion chamber every single second. The efficiency of the RS-25 engines, combined with the raw power of the solid rocket boosters, provides the precise balance of thrust required to push the heavy payload into a stable Earth parking orbit.
Okay, so the solid boosters and the core stage get the vehicle into Earth orbit, but they are still trapped in Earth's gravity well. They need one more massive push to actually intersect with the moon.
Right. That is the role of the upper stage, which for the Block 1 configuration is called the Interim Cryogenic Propulsion Stage, or the ICPS. Yes. The ICPS is powered by a single, highly reliable RL-10 engine. While it doesn't have the raw thrust of the booster stages, it operates in the vacuum of space where you don't need to fight atmospheric drag. The ICPS performs a maneuver called the Translunar Injection Burn.
The Translunar Injection, or TLI. For you listening, this is the critical moment. This is the burn that effectively raises the highest point of their orbit so dramatically that it stretches all the way out to intersect the moon's sphere of influence.
Which is nearly 250,000 miles away.
Exactly.
It is a precise, extended engine burn that imparts the massive change in velocity necessary to break free of low Earth orbit and set the spacecraft onto a highly accurate trajectory toward the moon.
And once the ICPS completes this burn, its job is done.
It separates, and the spacecraft is officially coasting through deep space.
Now, I have to ask about the overarching design philosophy here. I mean, the SLS is an absolute behemoth. It is incredibly expensive and complex.
Yeah.
Why do we need a vehicle of this specific massive scale just to return to the moon? Why not launch the mission in smaller pieces on commercial rockets and assemble them in Earth orbit?
Well, the strategic advantage of the SLS's immense payload capacity is that it enables direct delivery. By utilizing that 8.8 million pounds of thrust, the SLS can launch the fully fueled Orion spacecraft, the crew, and all their deep space life support systems in a single integrated launch.
Which fundamentally reduces mission complexity, because in spaceflight, the fewer times you have to rendezvous in orbit and execute complex docking maneuvers, the more elegant and efficient the mission architecture becomes.
Precisely. The SLS just powers through, doing the heavy lifting straight out of the gate. But beyond operational simplicity, this massive power is an active protective measure for the crew.
Oh, you're talking about the Van Allen radiation belts.
Yes. Surrounding the Earth are the Van Allen belts. These are vast regions of highly energetic charged particles trapped by Earth's magnetic field. Spending extended periods within these belts introduces ionizing radiation.
So how does the sheer power of the SLS mitigate that?
By utilizing the immense velocity imparted by the SLS and the ICPS, the spacecraft performs a rapid transit through the Van Allen belts. It accelerates the vehicle so powerfully that the transit time is dramatically minimized, brilliantly optimizing crew safety.
Okay, so the Space Launch System provides the sheer muscle, the unadulterated kinetic energy to hurl the payload out of Earth's gravity well. But once the ICPS separates, once they're out there past the Van Allen belts, gliding into the deep, silent cosmos, the rocket's job is over.
Completely over.
And now, the 4 astronauts rely entirely on their vessel to survive the incredibly harsh realities of the vacuum. And that brings us to the technological marvel that is the Orion Crew Module, which, for this specific mission, the crew has appropriately christened Integrity.
Integrity is a very fitting name for a vessel that operates flawlessly in the most unforgiving environment known to humanity. It is crucial to understand that Orion is not simply an upgraded capsule based on past designs.
Right.
It represents a quantum leap in aerospace engineering. It has been purpose-built from the ground up specifically for deep space operations.
Let's draw a distinction there because, to a casual observer, a spacecraft is a spacecraft. But the engineering requirements for a vehicle in low Earth orbit, like a capsule ferrying astronauts to the International Space Station, must be vastly different from a vehicle designed to travel to the moon.
The distinction is vast and fundamentally alters the engineering tolerances of every system aboard. In low Earth orbit, you are still within the protective envelope of Earth's magnetosphere, which shields you from the majority of cosmic radiation.
And you are also in constant, near-instantaneous communication with ground control.
Exactly. And most importantly, if a system anomaly occurs, you have the capability to execute a deorbit burn and return to the Earth's surface within a matter of hours.
You have a relatively quick return option, but in deep space, during a lunar transit, that quick return option completely vanishes. You are days away from home.
Yes. When you are 250,000 miles away, you require absolute, uncompromising self-sufficiency. The spacecraft must carry all of its own power generation, thermal management, deep space navigation, and robust life support systems.
Without any reliance on resupply.
Precisely.
Right.
And to achieve this unparalleled level of self-sufficiency, Orion utilizes a magnificent, highly integrated piece of international engineering, the European Service Module.
GESM. This is a massive, absolutely critical contribution from the European Space Agency. This isn't just a minor component, it is effectively the powerhouse of the entire spacecraft, right?
It is the absolute lifeblood of the vehicle. The Orion Crew Module, where the astronauts live and work, sits right on top of this service module. The European Service Module provides the primary propulsion for the spacecraft once it is in deep space.
It features its own main engine, along with an array of auxiliary thrusters for precise attitude control.
It also provides the electrical power for the entire vehicle via 4 large, highly efficient solar array wings that deploy shortly after launch.
But let's talk about thermal control, because managing heat in the vacuum of space is wildly counterintuitive. I mean, in our daily lives, if a computer gets too hot, a fan kicks on and blows cooler air over it, transferring the heat away through convection.
But in the vacuum of space, there is no air. You cannot use convection.
So how does the European Service Module manage the immense heat generated by the avionics, the life support systems, and the metabolic heat of 4 humans?
Well, thermal control in a vacuum is an extraordinary thermodynamic challenge. You are dealing with extreme temperature gradients. The side of the spacecraft facing the sun can reach scorching temperatures, while the side facing deep space plunges to hundreds of degrees below zero.
Right.
To manage this, the European Service Module utilizes an active fluid loop system, somewhat akin to the circulatory system in a human body.
Pumping a fluid to absorb the heat from the interior systems.
Correct. A coolant fluid is pumped throughout the Orion capsule, absorbing the excess thermal energy. This heated fluid is then pumped down into the European Service Module, where it is routed through large radiators mounted on the exterior of the spacecraft.
Oh, I see.
These radiators are coated in highly specialized materials that allow them to efficiently radiate the absorbed heat away in the form of infrared radiation directly into the vacuum of space.
So they use radiation rather than convection to shed the heat. And what about when they need to stay warm, like when the spacecraft passes into the shadow of the moon?
The system is entirely dynamic. By controlling the flow of the coolant and utilizing thermal insulation layers, the system can evenly distribute heat throughout the vehicle, ensuring all vital components maintain optimal operating temperatures during periods of solar eclipse.
It is a brilliant, continuously operating thermal balancing act. And the service module also holds all the vital consumables, right?
Yes, the highly pressurized tanks containing the water, the oxygen, the nitrogen, everything the crew needs to maintain a habitable atmosphere.
It really highlights the absolute necessity of international collaboration. We're combining the engineering brilliance of NASA's Crew Module with the incredible systems engineering of the ESA's Service Module.
It is a testament to the fact that deep space exploration is a unified global endeavor.
Beyond life support and thermal control, let's address the invisible environment of deep space, radiation. Once you are out in cislunar space, you no longer have the Earth's magnetic field protecting you.
Right.
How does Orion protect the crew from high-energy radiation penetrating the hull?
Well, heavy metals, like lead, which we use on Earth for radiation shielding, are extremely inefficient in spaceflight due to their massive weight. Furthermore, when high-energy galactic cosmic rays strike dense metals, they can actually create a secondary shower of radiation inside the cabin.
Oh, wow.
A phenomenon known as Bremsstrahlung radiation. So the solution lies in utilizing materials rich in hydrogen. Hydrogen atoms are incredibly effective at absorbing and dissipating the kinetic energy of incoming high-energy particles without creating that secondary scatter.
That is fascinating.
Orion utilizes advanced, highly dense polyethylene shielding, strategically integrated into the hull structure. Additionally, the spacecraft's internal layout is designed so that the crew can utilize the dense mass of their own water supply tanks and stowage bags to create a highly shielded storm shelter within the cabin.
Using the very water they drink as an active radiation shield. That is brilliant engineering.
It really is.
I want to pivot to the end of the mission because getting to the moon is a masterclass in adding kinetic energy, but coming home is an incredible display of removing it.
Absolutely.
When Orion returns from the moon, it isn't simply falling out of low Earth orbit, it is coming in on a lunar return trajectory. The physics of this re-entry are genuinely astonishing.
The return journey is a staggering display of orbital mechanics and thermodynamics. When Orion approaches Earth, it is hurtling through the vacuum at speeds approaching 25,000 miles per hour.
25,000 miles per hour.
That is roughly 40,000 kilometers per hour, or nearly Mach 32.
I want to emphasize how much kinetic energy is bound up in a vehicle of that mass moving at that speed. They have to shed all of that velocity to safely splash down in the ocean. And they use the Earth's atmosphere to act as the brake.
Yes. And hitting the atmosphere at Mach 32 generates an immense amount of energy. Orion is traveling so incredibly fast that the air molecules in front of the spacecraft simply cannot move out of the way fast enough,
So the air is violently compressed.
creating a brilliant bow shock just ahead of the vehicle. This compression violently heats the gas to the point where the atmospheric molecules transform into a layer of superheated, electrically charged plasma enveloping the capsule.
And temperatures on the exterior reach nearly 5,000 degrees Fahrenheit.
Yes, which is roughly half the surface temperature of the sun. To effortlessly manage that, Orion utilizes the most advanced heat shield ever constructed.
I understand it is an ablative heat shield, but how does ablation actually work? I mean, the concept of intentionally designing a critical component to burn away seems counterintuitive. How does burning up the shield protect the ship?
Ablation is a brilliantly effective endothermic process. The heat shield is composed of a specialized material called AV coat, an epoxy resin infused in a fiberglass honeycomb matrix. When exposed to the extreme thermal environment of the plasma wake, this material is designed to systematically char and melt.
Okay.
As the material undergoes this phase change from a solid to a gas, it absorbs a massive amount of thermal energy.
So the energy goes into changing the state of the material rather than conducting into the spacecraft interior.
Exactly. And as the charred material physically flakes away and is carried off into the slipstream, it takes all of that absorbed thermal energy away with it,
Sweeping the heat away from the vehicle.
ensuring that while the exterior is engulfed in 5,000-degree plasma, the interior crew cabin remains completely safe, cool, and structurally sound. It is a masterwork of thermal engineering.
It is a stunning piece of technology. Now, considering the immense complexity of everything we've just discussed, the life support, the thermal control, the navigation, the reentry protocols, I have a crucial question about the mission architecture. The Orion spacecraft is loaded with advanced avionics and redundant flight computers. It can execute this entire mission completely autonomously.
It can.
We definitively proved that with the uncrewed Artemis I mission, which flawlessly executed a lunar orbit and atmospheric reentry without a single human on board. So if the computers can execute the translunar injection, navigate the deep space transit, and manage the complex reentry profile, why put a human crew inside the capsule for this specific flight?
That is an excellent question, and it strikes at the core philosophy of human spaceflight. Autonomy is incredibly valuable for precision and baseline safety. Computers can execute complex propulsive burns down to the millisecond.
Right.
However, if our ultimate goal is to build a sustained, active human presence in the solar system, we must evaluate the human-machine interface in the actual deep space environment.
Because human adaptability is the ultimate redundancy system.
Precisely. We need to know exactly how these massive, complex vehicles respond to manual human inputs for a zero-gravity environment far from Earth.
I see.
During Artemis II, the crew will physically take manual control of Orion. They will test the translation and rotational hand controllers, evaluating the responsiveness, the ergonomics, and the interface displays of deep space piloting.
And putting a crew aboard places a genuine, dynamic, metabolic load on the environmental control and life support systems.
Exactly. We need to validate how the CO2 scrubbers, the thermal loops, and the humidity controls respond to the physical reality of 4 human beings living and breathing in that confined space for 10 days.
It is the ultimate necessary test drive before we commit to landing operations. And a sophisticated, boundary-pushing mission like this requires a crew that represents the absolute pinnacle of human capability.
It absolutely does.
Which leads us perfectly to the trailblazers themselves. Let's dive into the historic, incredibly accomplished crew of Artemis II.
This is undoubtedly one of the most inspiring and significant aspects of the entire mission architecture. Artemis II boasts what is arguably the most diverse, highly skilled, and symbolically powerful crew ever assembled in the history of spaceflight.
Let's break down the roster, starting with the individual responsible for leading this monumental endeavor, Commander Reed Wiseman. He brings a phenomenal operational background to the mission.
Commander Wiseman represents the ideal synthesis of engineering expertise and high-pressure operational experience. He is a veteran naval aviator, an incredibly accomplished test pilot who has flown a vast array of high-performance aircraft.
And in the realm of spaceflight, he brings invaluable experience from his extended duration mission aboard the International Space Station.
Yes, where he served as a flight engineer and conducted multiple complex spacewalks.
And as the commander, his role is ultimate oversight, correct? He isn't just a passenger. He is responsible for the overall execution of the mission profile.
Absolutely. His background in naval aviation ensures a profound understanding of complex vehicle operations under extreme physiological and psychological pressure. He possesses the calm, decisive leadership required to manage an entirely unprecedented deep space test flight.
The steady hand at the helm. Beside him, in the right seat, we have pilot Victor Glover, another incredibly accomplished aviator, a veteran of long-duration spaceflight on the SpaceX Crew Dragon.
Victor Glover's resume is exceptional. He holds advanced degrees in flight test engineering and systems engineering, providing him with a profound technical understanding of the spacecraft's internal architecture.
So he will be intimately involved in executing the manual flight control tests of the Orion module.
He will. But beyond his technical mastery, his selection marks a highly significant moment. He is making history as the first person of color to journey into deep space.
That milestone cannot be overstated. We are looking at a 50-year history of lunar exploration that was defined by a very specific demographic. Victor Glover's presence shatters a barrier that has stood for over half a century.
It really does.
It sends a resounding visual message to the entire world that the deep cosmos is a frontier that belongs to everyone.
It is a deliberate, vital reflection of NASA's commitment to ensuring that the next generation of explorers sees themselves represented in the ultimate human endeavor.
Absolutely. And speaking of shattering historical barriers, we have mission specialist Christina Koch.
Christina Koch's contributions to human spaceflight are truly staggering. She is an electrical engineer and a brilliant scientist. She currently holds the record for the longest single continuous spaceflight by a woman,
spending 328 consecutive days aboard the International Space Station, almost a full year in microgravity.
That gives her an unparalleled understanding of the physiological realities of spaceflight. Her scientific expertise and her deep understanding of human factors will be invaluable during the voyage.
She understands the long-term physiological adaptations and the psychological resilience required better than almost anyone.
Furthermore, she will be conducting critical scientific observations during the flight. And fundamentally, her role as the first woman to journey to the moon perfectly embodies the core spirit of the Artemis program, rightfully named for the lunar goddess.
It is poetic and entirely fitting. And completing this phenomenal quartet is mission specialist Jeremy Hansen. He is a fighter pilot, a physicist, and importantly, he represents the Canadian Space Agency.
Jeremy Hansen's inclusion is a masterclass in international diplomacy. It's a reflection of the deep collaborative architecture we discussed regarding the Artemis Accords.
Because his inclusion marks the very first time a Canadian astronaut, or indeed any non-American astronaut, embarks on a lunar mission.
The Canadian Space Agency has been an absolutely essential, indispensable partner in human space exploration for decades, primarily through their incredible contributions in space robotics, the Canadarm systems that built and maintained the space station.
Canada has essentially been the robotic arm of the international space community.
Precisely. By including a Canadian astronaut on this historic deep space flight, it solidifies the reality that Artemis is not a solitary national endeavor. It rewards decades of brilliant technological partnership. Jeremy Hansen will be heavily involved in mission planning, systems monitoring, and executing the complex operational timeline.
When you look at this crew Wiseman, Glover, Koch, Hansen, you are struck by the undeniable synergy. They aren't just four individuals. They are an impeccably trained, highly cohesive unit.
They have spent years undergoing exhaustive, unified training across facilities in the United States and Europe.
Spending thousands of hours in high-fidelity simulators, rehearsing nominal operations and highly complex flight dynamics.
They have simulated every single phase of the mission, from launch to splashdown, over and over again, forging an unbreakable team dynamic. That rigorous preparation ensures that when they are 250,000 miles from Earth, they operate seamlessly as one cohesive entity under the most extraordinary conditions.
Okay, so we have deeply explored the philosophy of the Artemis program and the permanent architecture. We understand the staggering muscle of the Space Launch System rocket.
The heavy lifter.
We've examined the advanced life support and thermal engineering of the Orion spacecraft, and we understand the brilliant, trailblazing crew ready to take the helm. Now, I want to walk step by step through the actual mission profile.
Let's do it.
Walk me through exactly what this monumental 10-day orbital ballet will actually look like from launch to splashdown.
The Artemis II mission profile is a beautifully choreographed, highly precise sequence of orbital mechanics. It is designed around a concept known as a hybrid free return trajectory.
I want to focus on that free return trajectory concept. I've heard the analogy of a boomerang used to describe it. You throw the spacecraft out there, it sweeps around the moon, and the natural gravitational forces pull it right back to Earth.
That's a great analogy.
Mechanically, how does that actually work? How do we use the moon's gravity to cancel out our outbound velocity and slingshot us home without firing the main engines?
The orbital mechanics involved are a brilliant application of physics. Instead of aiming directly at the moon to enter a stable lunar orbit, the ICPS translunar injection burn targets a very specific point in space, slightly ahead of the moon's orbital path.
Okay.
As Orion coasts outward, the moon's massive gravitational field begins to pull on the spacecraft, accelerating it and bending its trajectory.
It essentially catches the spacecraft in its gravitational wake.
Exactly. The spacecraft swings behind the moon, executing a figure-8 path. The moon's gravity alters the spacecraft's momentum vector, perfectly redirecting it back toward Earth.
Wow.
The immense advantage of this specific trajectory is that it is an inherent passive safety mechanism built directly into the physics of the flight path. Once that initial translunar injection burn is successfully executed, the spacecraft is on a guaranteed path back to Earth's atmosphere. It requires only minor, highly efficient trajectory correction burns to maintain the precise corridor.
It is using the momentum of the solar system itself as your primary safety feature. So let's trace the timeline. It all begins at Launch Complex 39B at the Kennedy Space Center. Walk me through the ascent.
At T0, the 4 RS-25 engines on the core stage ignite, followed milliseconds later by the solid rocket boosters. The SLS leaps off the pad with that 8.8 million pounds of thrust.
The vehicle executes a roll program to achieve the proper launch azimuth, right?
Yes. And as it ascends through the densest part of the atmosphere, it passes through max Q.
Yeah.
After roughly 2 minutes, the solid rocket boosters expend their propellant and cleanly separate,
Leaving the core stage to push them the rest of the way into Earth orbit.
The 4 RS-25 engines continue to burn, utilizing the cryogenic liquid hydrogen and oxygen. Once the core stage is depleted, it separates. Now the interim cryogenic propulsion stage and the Orion capsule are in low Earth orbit.
And after crucial systems checks, the ICPS ignites its RL-10 engine for that massive defining translunar injection burn.
The TLI burn. They stretch their orbit out to intersect the moon. Once that burn is complete, the ICPS separates, and they enter the outbound cruise phase.
During the outbound cruise, which lasts for several days, the crew is incredibly active.
Yes, they deploy the solar array wings on the European service module to begin continuous power generation. They execute a series of critical manual handling tests, evaluating Orion's translational and rotational control systems, while the spacecraft is still relatively close to Earth.
And this is where the psychological reality of the mission truly sets in. They will experience the profound visual shift of seeing the Earth transform from a massive landscape below them into a fragile, finite sphere suspended in the infinite darkness.
The overview effect.
Yes.
As they cross the vast distance of cislunar space, Earth's gravity slowly decelerates them, while the moon's gravity slowly begins to accelerate them. Eventually, they enter the lunar sphere of influence, setting up the most spectacular phase of the mission, the lunar flyby.
The lunar flyby. They will swing around the moon, passing remarkably close to the lunar surface. They are going to get unparalleled high-definition views of the far side of the moon.
They will capture incredibly detailed, high-resolution imagery and perform vital scientific observations. But this flyby phase also introduces a highly critical mandatory test parameter, the lunar occultation.
The occultation. What exactly happens during that period?
When the Orion spacecraft travels behind the far side of the moon, the massive, dense body of the moon itself physically blocks all line-of-sight communication.
Oh.
It blocks all radio frequency and optical laser signals to and from the deep space network on Earth. There's an extended period of complete, absolute communication blackout.
Complete silence from mission control. No telemetry, no voice communication, no ability for Houston to send commands. What are they actually doing during that blackout?
Mission planners view this occultation as a thrilling, meticulously planned operational test. It is the ultimate validation of the crew's autonomy and the spacecraft's robust, redundant design. During this blackout, the crew and the onboard flight computers are entirely responsible for the vessel's navigation, life support, and thermal management.
Gathering deep space operational data during this period of forced isolation is absolutely invaluable.
It simulates the communication delays we will inevitably face during future missions to Mars, proving that a crew can safely manage a deep space vehicle without constant oversight from ground control.
It is the ultimate test of human self-reliance. And once they swing around the curvature of the moon, they reacquire the signal, communication is restored, and thanks to the brilliant orbital mechanics of the free return trajectory, they are officially on the return leg, hurtling back toward Earth.
During the multi-day cruise back, they continue their rigorous schedule of continuous science. They study the ongoing effects of the deep space radiation environment, they evaluate the long-term performance of the life support swing beds, and they execute technology demonstrations.
And then comes the grand finale, re-entry. As they approach Earth, gravity accelerates them dramatically. They jettison the European service module, leaving only the Orion crew capsule.
They are preparing to hit the atmosphere at that staggering speed of 25,000 miles per hour.
And they hit the narrow re-entry corridor perfectly. The bow shock forms, the plasma engulfs the capsule, the AV coke heat shield ablates, sweeping the 5,000-degree heat away into the slipstream.
The spacecraft decelerates violently, bleeding off immense kinetic energy. Once they pass through the plasma blackout phase and the vehicle slows to subsonic speeds, the complex sequence of drogue and main parachutes deploy, stabilizing the capsule and gently lowering it to a highly precise splashdown point in the Pacific Ocean,
where a massive flotilla of specialized Navy recovery ships will be waiting to secure the capsule and welcome the crew home. It is 10 days of absolute edge-of-your-seat operational discovery.
It truly is.
But a mission of this magnitude, with this level of complexity, doesn't just happen in the vacuum of space. The impact of Artemis II reverberates across the entire globe, and the execution begins right here on the ground, long before the countdown clock hits zero. Let's talk about the immense scale of the ground operations and the global stage.
The preparation on the ground is a monumental, awe-inspiring achievement in its own right. In the months and weeks leading up to launch, the dedicated engineering and operations teams at the Kennedy Space Center execute exhaustive, microscopic checks of every single system on the vehicle.
We are talking about integrating the solid boosters, stacking the core stage, integrating the Orion capsule, and managing the propellant loading is incredibly complex.
Pumping hundreds of thousands of gallons of super-chilled liquid hydrogen and liquid oxygen into a 322-foot-tall rocket requires an intensely managed choreography of valves, pressures, and thermal conditioning.
And the launch control teams run fully integrated dynamic simulations.
Yes, ensuring they can manage any situation with absolute precision. And the crew readiness protocols are just as intense. They go through their final mission rehearsals, rigorous medical baselining, and then they enter strict quarantine protocols.
The quarantine is essential to ensure they do not introduce any terrestrial illnesses into the closed environment of the spacecraft. But this period also affords them vital, protected family time before they embark on this unprecedented journey away from the planet.
While the crew prepares, the technological infrastructure on the ground is gearing up to track them. The Deep Space Network, the array of massive radio antennas situated around the globe, has to maintain continuous contact.
But for Artemis II, they are testing a revolutionary leap in communication technology, aren't they? Optical laser communications.
Yes.
How does a laser system fundamentally improve upon traditional radio waves for deep space telemetry?
It represents a massive leap in bandwidth capability. Traditional radio frequency communication utilizes wide, long wavelengths, which naturally limit the amount of data you can transmit per second. Optical communications utilize near-infrared lasers, which have vastly shorter wavelengths. This allows us to pack exponentially more data into the transmission.
But the mechanical precision required for that must be absurd. You are talking about pointing a narrow laser beam from a spacecraft moving at thousands of miles per hour, nearly 250,000 miles away, and precisely hitting a receiver dish on the surface of a rotating Earth.
The pointing accuracy required is indeed staggering, utilizing advanced gimbals and tracking software. But the payoff is immense. By utilizing optical laser communications, we're dramatically increasing the data downlink.
We aren't just sending back basic telemetry.
We will be transmitting massive scientific data files and, crucially, high-definition 4K video streams in near real time.
Which fundamentally changes the public engagement aspect of this mission. We aren't just passively reading about this in textbooks or watching grainy, low-resolution CRT monitor footage like the Apollo era. We're going to have high-definition, crystal-clear video beamed directly to our phones and screens. The public gets to ride along in the cabin with the crew.
And that level of unprecedented access ensures that Artemis II will be a unifying global cultural event. Educational outreach programs, continuous live broadcasts, and real-time telemetry dashboards will allow millions of people worldwide to follow the intricacies of the mission.
It reignites the profound sense of wonder that defined human spaceflight, but updates it for a modern, highly connected, scientifically literate society. It is a powerful, undeniable message.
With the massive contributions from the European Space Agency and the Canadian Space Agency and the foundational framework of the Artemis Accords, it proves exactly what our society can achieve through shared ambition, transparency, and technological progress.
We are proving that the moon is within reach once again. But more importantly, we are proving that we are establishing the infrastructure for a future of sustained, peaceful presence off-world.
The successful execution of the Artemis II mission writes a brilliant, entirely new chapter in the ongoing story of human spaceflight. It is a chapter defined by remarkable engineering resilience, brilliant international innovation, and a shared, peaceful ambition to push the boundaries of what is possible. It reaffirms, with absolute certainty, that humanity's call to explore the cosmos is stronger and more unified than ever before.
Let's take a breath and appreciate the sheer magnitude of the journey we've just charted today. We explored the fundamental philosophy, the vital transition from flags and footprints to establishing a permanent multi-planetary foundation, utilizing the chemistry of lunar water ice and the diplomatic power of the Artemis Accords.
It really is a massive shift.
We analyzed the incredible towering muscle of the Space Launch System, understanding how those solid rocket boosters and RS-25 engines seamlessly generate an awe-inspiring 8.8 million pounds of thrust to perfectly push humanity out of Earth's gravity well.
The pure power of it is staggering.
And we examined the profound engineering ingenuity of the Orion capsule, the integrity, unpacking the thermodynamics of the European service module's active cooling loops, and the plasma-deflecting ablation physics of its heat shield.
A masterwork of engineering.
We met the brilliant barrier-breaking crew of Wiseman, Glover, Koch, and Hansen, understanding how their diverse backgrounds and expertise will evaluate the crucial human-machine interface in the isolation of deep space. And we traced the brilliant orbital mechanics of their perfectly executed free return trajectory, utilizing the moon's gravity to swing them safely back to a precise splashdown in the Pacific Ocean.
It is, without exaggeration, a masterwork of human endeavor. If there is a final overarching thought to draw from this entire architectural and operational marvel, it is a profound reflection on human resilience and our boundless capacity for innovation.
Absolutely.
Artemis II proves that our innate drive to explore the unknown, to expand our scientific horizons, and to unite globally in the pursuit of discovery is an unbreakable driving force. The engineering precision is flawless, the international diplomatic bonds are incredibly strong, and the call to venture farther into the deep cosmos continues to inspire us to reach higher and dream far bigger than we ever thought possible.
It truly does. At the very start of our conversation today, we talked about looking up at the night sky, how the moon always looks so distant, so untouchable, like a flat painting on the ceiling of our world.
And that's all about to change.
Because of the staggering engineering and human courage we've discussed today, that ceiling is going to have a permanent doorway. So I want to leave you with a final thought to ponder long after you finish listening today. Imagine stepping outside on a clear night a few years from now. You look up at the bright, glowing face of the moon and, for an absolute undeniable fact that human beings are up there right at that exact moment. They are living, they are working, they are utilizing the ice in the craters, and they're looking back at you. How will that fundamentally shift your understanding of our place in the enormous universe and what it truly means to be a citizen of Earth?